Alright, hello everyone, Professor Dustin here, and this video is going to be a solution to the whiteboard equilateral center of mass. So recall the setup for this problem. We have three particles, two particles of mass 2m and one particle of mass m, and they sit on the corners of an equilateral triangle of side length L, and I want to know where the center of mass of this system is. And so I think the hint is useful. Maybe try drawing the triangle first and guessing where the center of mass might be. It's always good to basically know the answer before you actually do a calculation, or at least know what to expect. So let's try to draw a picture of this system. You can pick an orientation for the triangle, it doesn't matter. I think the easiest one is the following. I'm going to put the little mass at the top, and put the bigger masses down here. And each side is length L. So that of course means that each angle is 60 degrees, because that's what an equilateral triangle means. And so I want to guess where the center of mass is. Well, the center of mass is the center of the object, where it will balance. So it's pretty clear that it has to balance about some point through the center, because that's where the axis of symmetry is. If you imagine the center of mass over here, there's no way that it would be balanced. It would be falling back and forth. So the center of mass has to be somewhere along that line in the middle. So now recall the thing we're trying to calculate. We're trying to calculate the center of mass. So let me write down the formula for the center of mass for three particles. So that's the center of mass formula for any arbitrary three particles, m1, r1, where r1 is the position of the mass 1 relative to some origin, m2 times r2, m3 times r3 divided by the total mass. Now in this center of mass formula, of course, this is a vector, it's a position, so that means that there are both an x and a y component of that position vector. So I'm going to write now the two equations which are contained within this one expression. So that's the position in the x direction, m1r1x, m2r2x, m3r3x divided by the total mass, and the same thing for the y direction, just with y's replacing all the x's. Now I want to evaluate those two expressions. In order to do that, I need to actually know what the x and y directions are. So I need to pick a coordinate system on this equilateral triangle. I'm going to pick one so that the answer is simple. There's a variety of different ways you can do it. You could do it so that the expression, so the actual work here is simple, so as many things here vanish as possible. What I'm going to do is I'm going to pick the coordinate system to be right in the center of one of the sides like this, the bottom side. Because since I expect the center of mass to be along this line, along the y direction, I expect the center of mass in the x direction to be 0. It has to be 0 to be along that line. So I'm going to guess that that is true and put my center of mass, put my origin right at that exact location. So now I should be able to figure out what the x and y components of each one of those vectors are. So let me draw in each vector I'm talking about. So let's call this guy, let's do color. Let's call that guy R1. Call that guy R2. And call that guy R3. So R1X, R1Y. Actually, because of my simple coordinate system, I can essentially just read off what those components are. R1 is only in the x direction, and its distance is half of one of the sides. So R1x is L over 2, and R1y is 0. It's similarly simple for R2. R2x is minus L over 2. R2y is 0. That's just because in the x direction, the component that goes in this direction is minus L over 2 because it's towards the left, and there's nothing in the y direction. Finally, I can write down R3x and R3y. For this mass, that vector R3 is only in the y direction. So the x component is 0, and the y direction, actually I have to calculate that because the y direction here is going to be the height of the equilateral triangle. So I'm going to need to use some trig to figure out what that height is. But that's actually not too bad because this is just a triangle. This is an opposite side to that angle. So that is going to simply be L sine 60. And in fact, if you remember your 30, 60, 90 triangles, the big angle will be 60. This is a 1, 2, 3, meaning the sides are 1, root 3, and 2. Whichever one goes opposite, the 60 must be the bigger one, so that's root 3, 1, and 2. You can check Pythagorean theorem, that works. 1 squared plus root 3 squared is 4. Root of 4 is 2, so that works. And sine of 60 is opposite root 3 over 2. So actually this answer here, the height is just root 3 over 2. You could also just put that into your calculator and get in a decimal how many times L that is. Okay, so anyway, now that I know the height of that thing, I can now say that the y component is root 3 over 2 times L, and I know what all the vector components are, and so now I'm ready to plug them into the two center of mass formula. So let's do the R component first. M1 is 2m. The x component, Rx1, is L over 2. M2 is 2m. The x component of that is minus L over 2. The last m is simply, so M3 is m. It has 0 x component, 0. Divide by the sum of the masses, 2m plus m. But you can see that 2m times L over 2 is canceled by 2m's times minus L over 2, and there's no contribution here. So this comes out to be 0, which is, of course, exactly what we expected, because that's why we picked that coordinate system in the first place. So now let's do center of mass in the y direction. That's 2m times the y component, which is 0, plus 2m times the y component, which is also 0, plus 1m, and that y component is root 3 over 2 times L. And that's divided by the total mass, 2m plus 2m plus m. Cool, now let's all simplify this. Those two guys are 0, so I'm simply going to get root 3 over 2, m times L, divided by the sum of the masses, 2m plus m, that's 5m. Doing a little bit of simplification, those two masses will cancel because they're on the top and the bottom. I'm just going to combine the 2 and the 5 to get my final answer. The center of mass in the y direction is root 3 over 10 times L. Cool, that's it. So in this coordinate system, the answer was indeed very simple. In the x direction, it is 0. In the y direction, it is root 3 over 10 times L. Now, depending on how you oriented your triangle, you might get a slightly different answer, but remember, the physical situation has to be the same. The center of mass will definitely be along the center of the triangle, starting from the small mass through the opposite side that connects the two larger masses, and the distance from that side of the two larger masses towards the center will be root 3 over 10 times L. Okay, that's it. That's been a solution to this equilateral center of mass. Thanks for watching, and I'll see you next time.